8.4 looks at dividing radicals and rationalizing the denominator. When we divide radicals, we're going to keep the same rules as when we multiply radicals. So what we're going to do is we're going to deal with the coefficients, and then we're going to deal with the radicands. So we're going to divide coefficient by coefficient, and then we're going to divide radicand by radicand. Just like in multiplying, once we do that, we have to remember that we need to simplify. That is key. So once we're done, we're going to simplify our radical and express in simplest form. So here's what this looks like. If I was working with variables and I had a radical b divided by c radical d, I would do a divided by c, and I could split that into the square root of b divided by the square root of d. I split and divide the coefficients, and then I split and divide the radicands. So let's say I had 3 radical 8 all over 9 radical 2. I would split the coefficients and do 3 divided by 9 times I'd split the radicands and do radical 8 divided by radical 2. 3 divided by 9 is going to leave me with 1/3. I don't move that 3 up to the top. It stays in the denominator, so it's 1/3. And then this simplifies into 8 divided by 4. This becomes the square, 8 divided by 2 leaves me with the square root of 4 in my numerator, which is just 2. So this is 2/3. That whole thing would simplify. Notice I divided coefficient by coefficient, I divided radicand by radicand, and then I simplified. One thing to remember is that because we're working with division, you can try one big radical or 2 little radicals, and I'm going to explain what I mean by that, because there's a little bit of flexibility here in what you want to work with. If you cannot simplify in 2 small radicals, make it 1 big radical, and if you cannot simplify the 1 big radical, make it 2 small. So you might have to ask yourself, did it work in 1 big? No? Okay, I'm going to try 2 small. Did it work in 2 small? No? Okay, I'm going to try it in 1 big. An example of this can be seen below. It says radical 20 divided by radical 5 is equal to, notice how I went from 2 small radicals, one in the numerator, one in the denominator, to 1 big radical that fits over top of the numerator and denominator, because 20 divided by 5 gives me 4, square root of 4 simplifies to 2. Or I start with 1 giant radical and the entire fraction inside, and I can split it into the square root of 144 divided by the square root of 16. Conveniently enough, 144 is a perfect square. This is 12. 16 is a perfect square, which is 4. The whole thing simplifies to 3. They won't always simplify into integers, but in this case, I had 1 big radical. I couldn't simplify this into something that would give me a perfect square. I recognize them as perfect squares, and so I split into 2 small radicals, which were able to be simplified independently of each other. Okay, let's look at the next part. When you're left with a radical in the denominator, we don't want to do that. It's not good math practice. So we need to do what's called rationalize the denominator. Think about what it means to be an irrational number. Something that goes on and on and on forever can only put as a fraction. Our radicals are irrational numbers. The square root of 2, the square root of 8, they're irrational numbers. So if that's left in the denominator, we don't want that there. So we're going to rationalize, make it a rational number. We do a little bit of a trick, some fancy numbers to make it work. It's going to be the same value but a different appearance. So like $5 bill and 5 ones. They're the same value, they just have a different appearance. So in order to do this, we're going to multiply the top and the bottom by the denominator radical. This process is called rationalizing. Here we are making it a rational number, the denominator. We don't care if there's a radical in the numerator but we do care if there's 1 in the denominator, right? Technically, if there's an irrational number in the denominator, that's not a rational number. We make it a rational number by rationalizing the denominator. So let's look at this first example. I have the square root of 35 over 15. I have one big radical right now. I'm going to see if I can simplify inside that. What I end up with is I could divide both of them by 5. So if I divide the top by 5, I'm going to be left with, you know what, let me do this. I'm going to divide top and bottom here by 5. It's really just a 1, divide by 5 on the top, and I get 7, divide by 5 on the bottom, I get 3. I can't simplify any further in one big radical. You know, let me just check. If I put it into 2 small radicals, square root of 7, not going anywhere. Square root of 3, not going anywhere. So that's going to be my final answer. However, I cannot leave a radical in the denominator. So what I do is I multiply the top and the bottom by the bottom radical. So I'm going to multiply the top and the bottom by radical 3 because radical 3 over radical 3 is really just 1. It's really just a giant 1. Remember that when I multiply by 1, I don't change the value, I just change the appearance. Think back to when we multiply radicals. I multiply coefficients, I multiply the radicands. Think back to when I multiply fractions. I multiply the numerators, I multiply the denominators. So radical 7 times radical 3 is going to give me radical 21, and radical 3 times radical 3 is going to give me radical 9. I go to simplify here. Radical 21 is not going to break down, so I'm left with the square root of 21 on top. But 9, square root of 9 simplifies into 3, and that is my final answer. I cannot cancel a 3 in the denominator with a 21. I can't cancel the 7 out of there, or 3 out of there, because the 21 is actually a radicand, and the 3 is a coefficient. They're not the same pieces. I cannot cancel those. It is not a coincidence that our denominator simplified into 3. It should always happen that way. If you try to rationalize the denominator and you're not left with a number that doesn't have a radical in the denominator, you did something wrong. Let's look at the next example. Okay, in the example, we're going to divide 6 radical 12 by 2 radical 3. I'm going to divide the coefficients by the coefficient, and then I'm going to divide the radicands by the radicands. So I have 6 divided by 2, and then I'm going to divide 12, square root of 12 divided by square root of 3. Well, 6 divided by 2 is going to leave me with 3 for my coefficients. And the square root of 12 over the square root of 3. I could try to break them down, but if I'm thinking a step ahead, I can put them in one giant radical. And 12 divided by 3 is going to simplify into the square root of 4. Square root of 4 is really 2. And this whole thing ends up simplifying into 6. There's no need for me to rationalize my denominator here because there is no radical in my final answer's denominator. Let me look at another example. Do this one over here. The square root of 7 over 2 times the square root of 5 divided by 3. If I look here, I'm stuck. I can't simplify this as one big radical. Even if I split it, square root of 7 over square root of 2, it's not doing anything. I can't go anywhere. And I'm going to realize the same thing is happening with 5 over 3. However, I realize they're asking for another operation. They're asking me to multiply. So I multiply radicand times radicand, coefficient times coefficient. These really have coefficients of 1. So when I multiply fractions, I multiply numerator times numerator. So 7 times 5 gives me 35, and I multiply denominator by denominator. 2 times 3 is going to leave me with 6. Okay, now I can break this down into either 2 separate radicals, or I can see if I can simplify one big radical. Off the top of my head, I'm realizing I can't simplify one big radical here. There's no factor they have in common that I can cancel out. So I'm going to split it into 2 small radicals. See if I can simplify here. Square root of 35 over the square root of 6. Thinking to myself, square root of 6 is going to break into 3 and 2. That's not going to get me anywhere. No one has a buddy and can leave. 35 is going to split into 7 and 5. Again, no one has a buddy and can leave. So this is going to be my final answer, so I need to rationalize my denominator. In order to do that, I multiply the top and the bottom by square root of 6, because this is really just a 1. Keep in mind that multiplying something by 1 does not change the value. If I ask you to do me a favor and I say your reward, you know what? I'll multiply all the money in your wallet by 1. There's no incentive for you. I'm not changing the value. I'm just changing the appearance, if that. Okay, so what I end up doing here, I multiply numerator times numerator, denominator times denominator, and then I say 35 times 6. Well, if I know 35 times 2 is going to give me 70, and that's going to be 3, this should end up being 210. Let me just double check my math there. Carry the 3, 18 and 3, 210. Square root of 210 all over the square root of 36, 6 times 6. That simplifies into the square root of 210 divided by 6. I need to check, can 210 be broken down? I can break it into 21 and 10, 5 and 2, 7 and 3. All my branches are prime and none of my branches are pairs. This is my final answer, the square root of 210 divided by 6. We're going to do plenty of examples in class, but here's what you want to remember. You can move back and forth between one big radical and two little radicals. So if it cannot be simplified as a fraction, try splitting them into a numerator and then the denominator and simplifying separately. If that cannot be done and you're left with something like this example here, square root of 7 over the square root of 3, you must rationalize your denominator by multiplying the top and bottom by your bottom radical. Once you do that, your bottom radical should become rationalized. Remember, we talked about the idea that a square root is really the 1/2 power. So if I'm squaring something, 1/2 times 2 is going to give me 1. My square and my square root will cancel each other out, and I'll be left with a rational number in my denominator.